The parent state has to have knowledge of all the different states that are out there. Um, and so that now whenever you're adding a new state, you have to add code to the parent state as well as creating the substate. Um, I realized that one thing I had forgotten about the active state transition is that each one of these states actually has to know which state that it has to transition to. And so whenever you want to add a new state, if there's a transition, let's say I wanted a new state called um, harvest substate 2, right? I would have to figure out exactly which states would transition to that and add code to each one of those. So it's a little bit more costly when you're adding new substates in an active state transition model. The child state compete it's actually much easier because, like I was saying, you have code in each child state that determines the relevance. So when you add a new substate, you don't have to add anything else to any of the other states because it's already computing which one is the best one at any given time. As I was saying, the parent state would actually need new code for each individual substate as you added them. So it's not quite as much as the active state, but it is still more than the child state. So in this case, like I was saying, you actually are considering the different substates and calculating which one is the most relevant at any given time. And you can either have this in the individual substates or in the parent state, using a simple heuristic mathematical formula to enable this. So one of the problems that you run into is that what happens if I'm in a current state and I want to transition to a new state, but I don't want to get rid of the state that I'm currently in. Two ways in which you can solve this problem is to have a stack. So you could have a state stack in which you basically deal with the new transition. So I'm patrolling and all of a sudden I get attacked and I want to retaliate. So I go ahead and retaliate, and once I'm done retaliating, then I go back and patrol. So that basically uses a stack. So you can either so in the case of the state stack, you would actually have multiple interruptions, multiple actions queued up one on top of each other, versus the alternate stack in which you would only have possibly one or perhaps multiple, but not a infinite number of actions queued one after another. So some of the advantages and drawbacks of state machine models that we've already talked about. So in each of these models that we've talked about, you can only be doing one particular action at any one time. So this becomes a problem in which, say, you want to move at the same time as you're attacking. What we went over so far doesn't really provide for that. You can't be in two different states at one time. Now, a way around this is to use multiple state machines. So you could actually have two different finite state machines controlling two different pieces of what I'm going to call for now tools, and you'll see why in the next slide. But basically, different parts of the AI agent. So in the case that I just mentioned, a weapon and the method of transportation. The example the book gives is Command and Conquer, where they have a tank, and so it makes sense to have two different models, one for movement and one for the actual cannon, turret, whatever you want to call it, so that they can act independently, except in occasions when they actually have to work in unison. And so this is a bit more code to deal with. It may not be the right solution, but it does provide for more flexible actions for your AI agents. And so one other model that I would like to talk about is goal-oriented AI. So in this, you're clearly defining your goals, you're clearly defining your action, you're clearly defining the method in which you are able to perform that action or a tool. And so basically in the last the last several models, we've only focused on the action. We haven't really focused on what is providing that action. Goal-oriented AI takes a little bit more code to achieve, but the benefit is that, as I was saying, with multiple state machines, you can have multiple goals going on at the same time, and all you really need to do is constrain what tool is used in each one of these goals. So if the tool is available and there's no conflict with any other goal that's going on at the same time, you can have multiple goals all at once. The benefit over the multiple state machines is that basically it's already abstracted away what the constraints are. You don't have to worry about coding in exactly how one finite state machine interacts with another finite state machine. It's already part of figuring out what the tools are. So in this example, we have a squad flank attack. Squad flank attack is made up of a couple different actions, or sub-goals we'll call them. So we have squad move to flanking position, and then they attack. So, the squad is made up of multiple agents, multiple models, or characters, whatever you want to call them. They each have a separate goal. So, Joe has to move to position 1, Jim has to move to position 2, Bob has to move to position 3, and so basically they have to get in that spot. Now each of them can move in different ways. So Joe basically can only walk. Jim has the ability to fly, and Bob also has the ability to walk. So there's different tools that are available to achieve this. In the case of Joe and Bob, they use their legs. In the case of Jim, he has a jetpack that allows him to fly. Now obviously if Jim didn't have a jetpack, perhaps he could meet this goal by walking instead of actually, flying. Now once all these goals are met, the other action can be achieved, which is the squad attack. So all three guys are in position, they can attack. Now obviously each one has a separate weapon, so they can all attack in different ways. So you can see that this provides for a lot more unique behavior, in that each agent is able to determine how they're able to achieve a goal at any one time, dependent on what tool they have and then the subsequent action that they can take. It also allows for very interesting situations where you don't have the tool available, and so that you can basically have your AI agent try and determine what the best action is, given the fact that they have a goal to achieve, but they don't yet have what the prerequisite to complete that goal. And so part of goal-oriented AI is figuring out